So far the dx in our integration notation has played no role in integration other than to indicate the variable of integration. But now it becomes convenient to make use of the dx. So consider this integral. Right now we don't necessarily know how to take the integral of this, but we just noticed in the previous example that 2x times e to the x squared is the derivative of this. So it makes sense that if we want to go backwards, so if we want to take the integral of this, it should equal this one, e to the x squared. So e to the x squared is the antiderivative of 2x times e to the x squared. So that means that the integral of 2x times e to the x squared should just equal e to the x squared. And then of course we can do plus c since we have that constant of integration. However, the only reason we knew that is because we just did that example previously, and so we kind of remembered, oh yeah, this looks like what we just found. This looks like the derivative of e to the x squared. So we know e to the x squared would be the antiderivative of this guy. But let's look at how we can actually calculate this without remembering that. So in this case, let's let u equal x squared. So now we need to figure out what dx equals. So we let u equal x squared, so then taking the derivative on both sides, we get du dx equals 2x. Now solving this for du, we have du equals 2x times dx. Now in the past, what I did was I would find dx. So in this case, dx would equal du divided by 2x. And so then I could plug that in right here for dx. And that would be fine. But if you notice, in my integral, I have this 2x and I have this dx. So I already have this 2x dx already in my integral. So I can just replace both of these guys. I know that if you multiply those two guys together, which they are, then it will equal du. So both of those guys will get absorbed into the du because du equals 2x times dx. So now we can make the substitutions. We let u equal x squared. So this part right here will equal u. And then the 2x dx will equal du. So that will give us the new integration, which is just the integral of e to the u du. So you can see here, I kind of rearranged the terms so it might be easier to see. So I put the 2x and dx right next to each other, and we know that together they equal du. And then we know that this guy up here equals u. So that's how we get this integration, just making our substitutions. That integral is very easy to calculate. It just equals e to the u plus c. But now we want our final answer to be in terms of x, so we replace u with what it equals, and we know u equals x squared. So now we have our final answer for this integral. It's just e to the x squared plus our constant c. So in this example, we were able to make the integration a lot simpler by our value for du. So it really mattered what we chose for u in this case. So since we let u equal x squared, it worked out perfectly. We found that du is equal to 2x dx, which we already had in the integration before, and so we were able to make that entire substitution work out. So in effect, we have applied the chain rule in reverse. The procedure is referred to as substitution or change of variable. We can recheck the result by differentiating. Now, many integrals cannot be solved using U-substitution, but any integral that fits the formula that we first showed, any of these three formulas here, can be solved with this U-substitution procedure. So the whole point with U-substitution is we would not know how to solve the original integral without using it. But when we use it, we come up with an integral that's more easily solved than what we started with. So we always want to choose u so that we attain an equivalent integral in which the original variables x and dx no longer appear and they're replaced with u and du.